Welcome back to pre-calculus, or to calculus, sorry. Welcome back to calculus. So here we are, we're doing surface area of a solid revolution. Entering this topic, this is just the final part of 7.4. There's the formula. We're not going to take the time to derive this. I'm going to talk it through. There are derivations out there, I'm sure, on YouTube, in our textbook as well, in 7.4, or maybe in appendix, I don't recall, but it's not one I really feel the need to get into. I'm going to talk about it, though. So it looks familiar, hopefully, to you, because you have this right here, looks like what we did with arc length, right? That looks like the arc length portion, the integral of that, dx. But you have this extra 2 pi and r. 2 pi r, that sounds familiar. That's circumference, right? So these are going to be ones where I'm going to advise you to make a sketch. Probably not quite as crucial as washer and shell, but it'll be helpful. So here's my sketch here, just a random function that I came up with from A to B. Now if you imagine this being revolved around the x-axis, then it's going to end up looking like something like this. Something like that, right? So this is not a volume, but a surface area. So can you imagine that surface? Just imagine not a representative rectangle here, but now we're going to have a representative point, like here or something. Imagine that point revolving around. It ends up down here, and you're having that surface. So if you want to find the area of the surface, really interesting what we do here. We do the arc length, which is this part, times 2 pi r, which is circumference. And if you imagine, this is going to make, as that revolves around, it makes a circle. What would the circumference of that circle be? It'd be 2 pi r, where r is that distance there, right? And r is obviously changing, so I'll call it r to x, just like they do. And so you're multiplying that circumference by the arc length, which is that. So this reminds me a lot of the formula for the volume of a cylinder. And I drew it sideways to make it look kind of like this. If you take a cylinder, like a soup can, you tear the label off, then this dimension here is what? That's the circumference, 2 pi r. This dimension is the height. It's 2 pi r times the height. Well, what is the height here? Well, the height is not this distance necessarily because it's a curve. It's the arc length. So that's a kind of a rationalistic why it works. You don't really have to think that through, but that's where it comes from. Let me tell you what P is before we go on. Just give you a somewhat formal description of P. So P is, not P, sorry, R. I'm thinking of shell. R is the distance, well, you can see it on the picture there, from the representative point, I call it, to the axis of revolution. So really, it's like R in disk or washer method. So we're seeing all of these kind of having some shared ideas. Okay, let's do a couple examples. This first one is in your book, page 474, number 43. And they actually have a sketch for you. I'll do it as well, but it's the equation y equals the cube root of x plus 2, and here I'm using y, I could call it f of x. And we're only going to look at this from 1 to 8. Well, from 1 to 8, the cube root looks kind of like the square root. So I will try to make a sketch of this. So the y-intercept is 2, and we're only going to draw it from 1. So it's going to look like this. Something like that, to 8. And we're going to revolve that. Did I say? I didn't say. Revolve around the y-axis. Okay, let's get some color going here. So if we revolve around the y-axis, this thing, you don't have to draw the mirror kind of image over here, but I guess I'll do it on a few of these. So the representative point would be like here, and it would revolve there. So can you visualize that? Kind of has that shape to it. And our R is that distance there. I didn't mention this before, I should have, but we're going to always do dx on these. So it's kind of interesting. Sometimes there are, like in this case, will just be x. Sometimes it might be the function, we'll see in some later. Okay, so I think we got it ready to go here. So our surface area, I'm going to use, as you saw before, capital S, and try to make it not look like an integral, so kind of make it wide. 2 pi times the integral from 1 to 8 there we go, then it's r, let's see if I can get the equation up here, there we go, then it's r, and the radius is just the x value, right? Because you could think about different places the representative dot could be. It could be here, it could be here, it could be here, whatever it is, it's always x units from the x-axis. So we just put an x there, times the square root, dx on the end, 1 plus, what did I forget to do? I didn't do the derivative, right? Better do that. So y prime is 1/3 x to the negative 2/3. Okay, so that will be 1/3 x to the negative 2/3 all squared. Okay, do a little cleanup on that. So again, these aren't as hard to set up, but the this is the same thing, but the work is going to be in getting the integral. And here I'm just doing some simplifying first. I probably could have started here rather than with that negative exponent. Okay, so this is 1 over 9x to the 4/3. Don't forget the dx. Now it seems we're stuck. Well, what if we just got a common denominator down below? That might not be a bad idea. The common denominator would be 9x to the 4/3. So with 1, it'd just be 9x to the 4/3 over 9x to the 4/3. Doesn't look that great, does it? But what we can do is we now, this fraction, you can square root the denominator. So I can square root it and bring it out. Not in front of the integral, but at least in front of the square root. And this, it just works out really nicely. So I have x, that thing comes out as 3x to the 2/3. You may still feel discouraged. This is really not getting us anywhere, but hang in there. You know what, let's bring that 3 all the way out. The 3 doesn't have any x in it, so we can do that. And then x over x to the 2/3 is x to the 1/3. So you think we did anything worthwhile there? I mean, we still can't integrate it, can we? But hopefully something stands out to you here. Something we've looked for ever since we started integrating this and that. What's true about those two things? I mean, think of all the integration techniques we have. Kind of our go-to move is u substitution, and one of the main things we think of in u substitution is you're looking for good u du pairs, and those are often things separate by 1 degree. So what if we let our u be 9x to the 4/3 plus 1, and usually you want your u to be the thing in the most difficult position, the thing in peril. And under the square root or a denominator are two of the most common things we let u become. Then our du is going to be 9 times 4/3 x to the 1/3. I don't want that 9 to the 4/3, but we can, that's 36, that's, 36 over 3, which is 12. That just becomes 12. So I could do this, 1/12 du equals x to the 1/3. Can you believe it? dx, don't forget dx. So look what we got here. This is now square root of u. The dx becomes 1/12 du. Our bounds are going to change. 9 times 8 to the 4/3 plus 1. 9 times 1 to the 4/3 plus 1. Let's bring that 1/12 out front, so it becomes 2 pi. I'll take my time in reducing that. This integral is now, what is that going to be? Just look over here. It's going to be 145 and 10, because so 8 to the 4/3 is 2, 6, 8 to the 1/3 is 2, the 4th is 16, 16 times 9, 144 plus 1, 145, and this is going to be 10. Wow, we've really done some good work here. This can reduce there, so we end up with pi over 18 times, this becomes 3/2. Gotta put a 2/3 out front. 145 and 10. Now it's pi over 27. And not a lot's gonna happen here. 145 to the 3/2 minus 10 to the 3/2. Let's just call it good right there as our exact surface area of this. So, oops. Hope that is helpful. That was pretty long. But yeah, that's going to be a pretty common type integration move we're going to use. So you might make note of that one. Okay, let's do one more. This will be the last one from section 4, really from chapter 5. And this is one in the book as well. This is on page 475. It's number 56. It's a word problem. It says, a right circular cone is generated by revolving the region by y equals hx over r, y equals h, and x equals 0 about the y-axis. Verify that the lateral surface of the cone is, I'll write it down in a second, and it gives it to you. Okay, so let's write out what that means. So it says a cone, you can create a cone by revolving the line y equals, this is what they say, hx over r. I don't like that too much. I'm going to make that y equals h over r times x. Okay, so clearly h over r is your slope, x is your input variable. Okay, so if h over r is your slope, well, we know it's going to go through r h somewhere. And you're going to revolve, so let me keep reading. It says, revolving this, also y equals h. Just goes right through there. Also x equals 0, which is this. You see your region is that triangle, and it's revolving that region about the y-axis. So we're going to revolve it about this axis. Okay, as much as I want to shade this, it doesn't really need to be shaded. We can just make a representative dot there. And as it revolves, it's going to look like this. Kind of run that space there. And that representative dot, of course, would pop up over here. So, see the cone? There's kind of the top of the cone right there. Wow, terrible. Okay. And we want to find that, we want to confirm the surface area is this. This is our goal. Surface area is pi r square root of r squared plus h squared. Just to make sure I write down all the equations they gave you in case you didn't hear me say it verbally. They also said y equals h, and they also said x equals 0. So those are given. That creates that triangular region, and we're revolving around the y-axis. Okay, and we want to get the equation there for surface area in red. So what we need to do first is take the derivative. Let's do that. And the way I wrote it, I think makes the derivative really easy to show. It's just h over r. It's like the derivative of 5x is 5. This form, I think, would be a little bit more confusing. Okay, so we're ready to set up. Let's set this thing up. I'm just going to work in black. So the surface area is 2 pi integral from, where's it from? It's going to be from 0 to r. You have to imagine your dots. This dot is moving up the region there. Also this, it's a dx problem. All these are dx, so you're giving x bounds. What is our r value? The distance to the axis of revolution, which is just x. And then we have 1 plus the derivative squared. What's kind of interesting about this? The thing in the square root doesn't even have any x's in it. It can pass right through the integral. I didn't actually do this in my note I'm looking at, but I think it'd be wise to just get it through there. So this is 1 plus h squared over r squared. Okay. So I guess we can go ahead and take that integral while I'm simplifying here. I'm going to do like I did before. I'm going to get a common denominator, which would be r squared. And this does become 1/2 x squared from 0 to r. So this one's going to be considerably easier than the last, although some similar things. This move right here happened on the last one as well, right? Okay, so this becomes, first of all, just like before, that is square rootable. It can come out. So we now have 2 pi over r times the square root of r squared plus h squared. Oh, that 1/2. Put that over there. Okay, from that 1/2 right here. So those cancel with this too. And then we can plug in, and we plug in r squared minus 0 squared. Okay, are we going to get there? There's our goal. Looking okay. So we have pi over r, that becomes r squared, times r squared, times, looking good, isn't it? That's going to cancel, become r with that. And yes, we got it. We got pi r times the square root of r squared plus h squared. Check. Okay, well that is surface area. Hopefully that helped clear some things up. How we get r, where the formula kind of comes from, and really the integration process and how it's usually ideal to simplify under the square root, pull out that